Hi everybody, welcome to another video in linear algebra, section 7.1, diagonalization of symmetric matrices. So a symmetric matrix is a matrix A such that A transpose is equal to A. So let's look at some of the matrix here. So symmetric, as I said, when A equal to A transpose. So because of that, A has to be a square. So symmetric matrix has to be a square matrix. Because if it's not, the dimension will not match. We have to have from m by n, then it will be n by m. It will not match. So it have to be a square matrix. So now it's same number of rows, same number of columns. And then A transpose equal to A. So the reason we call that symmetric because the entry on the diagonal, it will symmetric on the diagonal. As you see, all the entry on the diagonal are fine, but 2 and 2 are symmetric, -3 are symmetric, 5 and 5 are symmetric. So that's why we call it is a symmetric matrix. Of course, when we transpose, it will be the same. Now when we transpose this, row becomes column, and column becomes row. Yeah, I just write the first row, first column become the first row, and that. So this is symmetric. So we put check mark here. This is not a square, so it cannot be symmetric regardless of the entry. This one, -1 and 3 on the diagonal, I mean it will be symmetric to that. If we do transpose, we will have -1 and 2 become the row, and then 2 and 3 become the column, and they're equal, right? So yes, it's also symmetric. And on this one, if we draw the diagonal, they are not symmetric to -2. Because if we do the transpose of that, the first column becomes the first row, and they are not the same, so they are not symmetric. It's so easy to see if the matrix is symmetric. It will symmetric on the diagonal. Right. Now, when a matrix is symmetric, it does have some nice properties. We'll see related to that, of course, is diagonalization. So let's diagonalize this matrix and see what can we see. What do we get from there? Of course, the same way we do before. First, find eigenvalues, eigenvectors, and then we can diagonalize it. So first, find eigenvalues. Which means we solve the equation determinant of A minus lambda I. So we will have determinant of the matrix A 6, -2, -1, -2, 6, -1, -1, -1, and 5. We find the determinant where we subtract the lambda on the diagonal, and let's just evaluate along the first row. So first we have 6 minus lambda. The sign will be positive, and after that we will have the submatrix. We evaluate along the first row. So what's left is 6 minus lambda, negative 1, negative 1, 5 minus lambda. Right, next is negative 2. The sign chart will be plus, minus, plus, so that will be subtract. And for negative 2, the submatrix, the cofactor, negative 2, negative 1, negative 1, 5 minus lambda. And then the last one is minus 1, will be a plus. The submatrix, negative 2, 6 minus lambda, negative 1, negative 1. Right. So we have 6 minus lambda, and then we have 6 minus lambda, 5 minus lambda, minus 1, plus 2, minus 2, 5 minus lambda, minus 1, minus 1, 2, plus 6 minus lambda. Right, let's multiply them out. Here we have 30 minus 1, that will be 29. Minus 5 lambda, minus 6 lambda, minus 5 lambda, minus 11 lambda, plus lambda square. Plus 2, minus 10, minus 1, minus 11, plus 2 lambda, minus 1, 2, plus 6, 8, minus lambda. Right, multiply them all out. Multiply by 6, 6 times 29. $174. Minus 66 lambda plus 6 lambda square minus 29 lambda plus 11 lambda square minus lambda cube minus 22 plus 4 lambda minus 8 plus lambda. Right, I'm just going to get the characteristic polynomial. Right, let's simplify. We only have one cube. And a square, we have 6, 17, and that's all. And then the lambda, negative 66, negative 29, 4, and 1. Let's draw negative 66, negative 29, plus 4, and 1. Minus 90, and then 174, minus 22, minus 8, 144. Right, so that is a characteristic polynomial. We do, of course, solve the equation equal to 0. Right, so we get this equal to 0. So do that. I'm just going to put on the graph negative x cubed plus 17 x squared minus 90 x plus 144. Right, look, that go to 3, 6, and 8. See, eigenvalues 1, 2, and 3. Because we can just go to the table. So yeah, it does 3, 6, and 8. So yeah. Right, so now we find the eigenvalues. Try to write small. This problem takes a lot of space. We have eigenvalues already. Now we find eigenvectors. Which is solving the equation a minus lambda I times x equal to 0. Right. So first we have the eigenvalues of 3. So I'm going to subtract the matrix. 6, negative 2, negative 1, negative 2, 6, negative 1, negative 1, negative 1, and 5. Of course, we have to subtract 3, the eigenvalues on the diagonal, and multiply by x equal to 0. That equivalent to the matrix of 3, negative 2, negative 1, negative 2, 3, negative 1, negative 1, 1, and 2. And do reduce to echelon form. Yeah, just copy it wrong. Right, so that's what we have. 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0. Right, so simple enough. Pivot here and here. x1 minus x3 equal to 0. x2 minus x3 equal to 0. And x3 is 3. Right. So with that, we write the solution x equal to x1, x2, x3. x1 move the x3 over, and move the x3 over, and factor out x3. Of course, we choose 1, 1, 1 to be the eigenvector. So the eigenvector corresponding to lambda equal to 3 is going to be 1, 1, 1. Right, so that's the first one. There will be space in the next page. Similarly, we find eigenvectors for eigenvalues of 6 and 8. Right. So first the matrix 6, -2, -1. And subtract 6 on the diagonal, the eigenvalues. Times x equal to 0. That is equivalent to 0, -2, -1. The nice thing about this is we can just copy the previous one, or we just hit second enter, and we only need to change the diagonal. It will be 0, 0, and -1. Right. So we will have 1, 0, 0.5. So we have x1 plus 0.5, x3 equal to 0, x2 plus 0.5, x3 equal to 0, and x3 is 3. Right. So with that, we can write the solution as x is x1, x2, x3. Equal to x1 is -0.5, x3, x2 is -0.5, x3, and x3 is 3. So factor out x3, we have -0.5, -0.5, and 1. Of course, when we choose for eigenvalues, eigenvector, we choose something to be simple, without fraction or decimal. So let's choose x3 to be 2. So that we have x, the eigenvalues. 6 will give us the eigenvector of -1, -1, and 2. Right. Now for the eigenvalues of 8. Actually, this we write a lot, but actually we didn't do many calculations. Right, -2, -2, -1, -2, -2, -1, -1, -1, and -3. Right, reduce row echelon form. So in this case we will have this will be -3, -3, and -3. As cannot be, because we're not supposed to have trivial true solution. I just entered wrong. That's okay though. Right, much better. Right, so I have x1 plus x2 equal to 0. x3 equal to 0, and x2 is 3. So with that we have x equal to x1, x2, x3. x1 equal to negative x2, x2 is 3, and x3 is 0. x2 is 3, sorry. Factor out x2, we have -1, 1, 0. Right. Of course that will be so the eigenvector corresponding to that is -1, 1, and 0. Right. So that's good. We have eigenvalues, eigenvectors. Put all of that together, we can diagonalize the matrix. But I want to do one step further. Now we have the eigenvectors 1, 1, 1, -1, -1, and 2, -1, 1, and 0. Right, so what we have, then we put in the matrix. That should be easy. But what I want to do is a little bit different. Now let's just write the 3-vector eigenvector. 1 is 1, 1, 1. 2 -1, -1, and 2, and 3 -1, 1, and 0. Right, so what's so special about this? Now, observe that they are orthogonal to each other. We can check x1 dot x2 be -1, -1 plus 2, so that equal to 0. Now x1 dot x3 -1 plus 1, 0, so that also 0. And then 2 and 3. So 1 plus 1, I'm sorry, plus 1 minus 1, 0. So x1, x2, x3 form the orthogonal basis. They are orthogonal, so they will be linearly independent, and therefore they will form a basis. So this is the set form orthogonal basis. Now let's do one step further and normalize x1, x2, x3. I try to write very small here. Hopefully it will be enough. Normalize x1, x2, x3. Right, so u1 equal to x1 over the norm of x1. Right, x1 is 1, 1, 1. The norm of x1 is square root of 1 square, 1 square, 1 square. Sorry, I had to write very small because we don't have much space. So we have 1/3, 1 over square root of 3. Right, let's normalize u2, normalize x2. x2 is -1, -1 and 2. Right, and then divide by the magnitude. Right, 1, 1, and 2 squared 4, so it's square root of 6. And then u3, normalize of x3. -1, 1, and 0. -1 square, 1 square, and then 0. -1 over square root of 2, 1 over square root of 2, and 0. Right, so we do form the orthonormal basis of those three vectors. Now, what's so special about that? Now recall that if we have orthogonal, Q is orthogonal matrix. By the way, even though we call that orthogonal matrix, we actually mean it is the matrix whose columns are orthonormal vectors. Orthogonal matrix whose columns are orthonormal. Not orthogonal. So we have to use U. Cannot use this vector, have to use the normal version. Orthonormal vectors. And when that happened, we have and Q inverse will be equal to Q transpose. So this is a very nice property. Remember the diagonalization in general, we can say A equal to PDP inverse. P, of course, the vector when we stack all the eigenvectors, and D, the diagonal matrix of eigenvalues, and then P is P inverse. If we have to do that, we have to find inverse. So if we use those metrics and we have to find inverse, and I mentioned this many times, inverse is very expensive operation. By expensive, I mean it will take a lot of time to actually find inverse. Normalize the vectors is very simple way to do, right? So in that case, instead of writing the inverse, we're just going to use the transpose. Transpose is a lot easier than to do than the inverse, almost effortless, right? Because of that. So instead of A equal to PDP inverse, we will use this is called the diagonalized orthogonal diagonalization. We use Q D Q transpose. That will be a lot easier to do, right? So we have Q. So in that case, Q is going to be the matrix where we write this in column. This one a little bit bigger. So that is Q, and then D, of course, that's just the matrix of the diagonal matrix of eigenvalues. Notice 1, 2, 3 have to be consistent. So here, eigenvalues of 3, 6, and 8 in that order. And then we just do this matrix transpose. Will be easy, right? Row become column. Row become column. Right. And this is called orthogonal diagonalization, meaning we use the orthogonal matrix to diagonalize it. Right. This only works for symmetric matrix, as we'll prove that in the next theorem. But of course, what we do is find eigenvalues, eigenvectors like we normally do. But when the matrix is symmetric, we can find the orthonormal basis. Therefore, we can find the matrix, orthogonal matrix to that. So instead of just any vectors, any matrix of eigenvectors, we specifically use the orthogonal matrix, meaning the matrix of orthonormal vectors. And with that, we don't have to find inverse of this. Finding inverse of this is a lot of work, especially with all the square root and all. So just do the transpose. Right. So that's an advantage of having the symmetric matrix. We do not have to do the inverse. Imagine if you have to do the inverse of 5 by 5 by hand, even though the values are simple like this. There's still a lot of work. Normalized vectors are very easy to do, even though the number is not very friendly. But after we normalize it, we just do the transpose instead of the inverse. That will be a lot easier to do. Right. Now, theorem. If A is symmetric, then any two eigenvectors from different eigenspace are orthogonal. Right. So in that case, let's say we have this pair of eigenvalues and eigenvector. Let lambda 1 x1 and lambda 2 x2 are pairs corresponding eigenvalues and eigenvector of A. Right. So if we have eigenvalues lambda 1, we have eigenvector x1. If we have eigenvalues of lambda 2, we have eigenvector of x2. Right. We need to show that the eigenvectors are orthogonal. Need to show that they are orthogonal, and they are orthogonal, so the dot product will have to be equal to 0. Right. So that's what we need to prove. Right. That's very simple actually. So let's say the dot product x1 and x2. Kind of difficult to do that, so I will say is equal to x1 transpose x2. That is the definition of dot product. But we're going to utilize, and I put lambda 1 here. Still doesn't do anything. The number times the vector or number times the matrix, we can just put the number into the matrix and then we transpose it. It's no problem, right? And then x2. Now, by definition, because this is the eigenvalues and eigenvector, that gives us a times x1, right? Because eigenvalues and eigenvector satisfy the equation ax equal to lambda x, that eigenvalues, eigenvector. So that's exactly what we have here. Lambda 1 x1 is ax1 transpose x2. Now, the transpose of a product is the product of transpose, but in reverse order. So it will be x1 transpose a transpose x2. Now, next we invoke the given condition that A is symmetric. So instead of A, we can just use A. Because from here to here, A is symmetric. So A transpose is equal to A. And now we group this together. A and x2. Also, the equation of eigenvalues and eigenvector, we will write that equal to x1 transpose A, x2 transpose is going to be lambda 2 x2, and this is a number I just move in front with no problem. Alright, just move the lambda 2 in front. Now that equal to that. If we move both of them on the other side, so we have lambda 1. Just say this is equal to lambda 2 x1 dot x2. So at lambda 1 x1 dot x2 subtract lambda 2 x1 dot x2. If we factor out x1, move that to the other side, that will be equal to 0 because they are equal to each other. The difference will be equal to 0 number, not 0 vector. Now factor out the lambda 1 and lambda 2. We have x1 dot x2 equal to 0. Now, what we have is the two eigenvector from different eigenspace. Because it is from different eigenspace, the eigenvalues are different. If this is not equal to 0, the only thing make this equal to 0 is the dot product has to be equal to 0, and that's what we need to show. Right, that's what we need to show. So when we have the symmetric matrix, then the eigenvectors from different eigenspace have to be orthogonal, meaning that a vector here corresponding to different eigenvalues, those two guarantee to be orthogonal. Right. So here's him. An n by n matrix is orthogonally diagonalizable if and only if A is symmetric. Okay, that's what we show here. That is A equal to Q D Q transpose, where Q is orthogonal matrix, meaning that the columns are orthonormal. And notice that it have to be orthonormal. Orthogonal is not enough. Right. Let's do another example. Probably won't have enough time or space to complete the problem because this takes even longer time. But this time we are given eigenvalues lambda 1 with multiplicity of 2 and lambda 2 is negative 2. Right. So let's just find the eigenvectors because we already have the eigenvalues. So eigenvectors. To do that, we solve the equation a minus lambda I times x equal to 0. Right. For lambda 1, let's say because multiplicity of 2, so customary sometimes we do like this. We say this is lambda 1 and 2 because they have multiplicity of 2, and just change this to 3. So we have, yeah, just write like that. So for lambda 1 and 2, because they are repeated, of 7. So we will solve the equation, the matrix A. We won't be able to complete this problem, but at least I'll just show you the idea when we have something like this. Right. Subtract the eigenvalue on the diagonal, which is 7 in this case. Would give us the augmented matrix of negative 4, negative 2 and 4, negative 2, negative 1 and 2. They look the same. 4, 2 and negative 4. Actually they're all the same. By the same I mean multiple of a vector. Right. Reduce for echelon form. Negative 4, negative 2 and 4, negative 2, negative 1 and 2, 4, 2 and 4. Right. Yeah, that's what we expect. 1, 0.5, negative 1. The rest are 0. Right. With this, we only have x1 is the pivot for x1. The other x2 and x3 are free. So we have x1 equal to x1 plus 0.5, x2 minus x3 equal to 0, and x2, x3 are free. To write the solution, we have x equal to x1, x2, x3. x1, subtract this to the other side, negative 0.5 x2 plus x3. x2 is free, x3 is free. So put like that, so we can just split the vectors. Factor out x2. So we do have two eigenvectors here. Now, of course, we choose x2 to be something that is, so we don't have fraction, so choose x2 to be 2. We have the first eigenvector of negative 1, 2, and 0. And then x3, we just choose x3 to be 1. So we have x3 equal to 1, 0, and 1. Sorry, x2. So for the eigenvalues of 7, multiplicity of 2, there are two corresponding eigenvectors of that and that. Right. Now we find the eigenvalues for negative 2. Three, negative 2, 4, negative 2, 6 and 2, 4, 2 and 3. Now subtract negative 2, meaning we plus 2 on the diagonal. X equal to 0. Right, that gives us the romantic matrix of 5, negative 2 and 4, negative 2, 8 and 2, 4, 2 and 5. Right. I just need to change the diagonal. Right. So we have x1 and x2. x1 plus x3 equal to 0. x1 plus 0.5 x3 equal to 0. And x3 free. Right. So we write the solution x as x1, x2, and x3. This is a very long problem. We won't be able to finish that, but you see the idea. When we have something like this, what should we do? So x1 negative x3 and x1 is negative 0.5 x3. x3 is free, and factor out x3, -1, -0.5, and 1. Right. Now it's easy. We have to deal with fraction. Could even choose negative if we want to. But I just choose x3 to be 2. That's enough to take care of the fraction. So the eigenvalue 3. The reason I use 3 because corresponding to the eigenvalues of lambda 3. So multiply everything by 2. Now, with that, we found the eigenvectors. Now, what's next? Right. What next is we verify that if they are from the the orthonormal basis. And in this case, it does not. That is the problem. Notice that we have two eigenspace, one corresponding to eigenvalues of -2 and one corresponding to eigenvalues of 7. And the theorem says that this one and that one will be orthogonal. We can verify easily. Do the dot product. 2 minus 2 is 0. That's good. This one minus 2 plus 2 is 0. Yes. So x3 orthogonal to x1 orthogonal to x2 because they're from different space. These two on the same space, and when we multiply, that's -1. Well, they do not form. These two are not orthogonal with each other. Let me write the note here. Note that x3 orthogonal to x1 and x3 orthogonal to x2 because now x3 on different space, eigenspace than x1 and x2 because x3 is on the different a different eigenspace. Yeah, eigenspace corresponding to the eigenvector, eigenvalues of -2. That will give us x3 and the other two on different space. And x1 and x2 on the same eigenspace. The theorem doesn't guarantee that they will be orthogonal. So say x1 is not orthogonal to x2 because they are in the same eigenspace. Meaning they're not necessarily orthogonal. I mean, they could probably still can be orthogonal, but in general it's not, and we check they're not. Right. So in this case, if we want to, we have to find the orthogonal or orthonormal basis using the Gram-Smith process. So if we want to work further, like I said, that's why this takes too much time. So we need Gram-Smith process to convert from x1 and x2 to v1 and v2, where v1 orthogonal to v2. Yeah. So the Gram-Smith process will turn any two vectors into orthogonal vectors still in the same space, spanned by those two vectors. So we do the Gram-Smith process, which by itself take a lot of time either. But when we do the Gram-Smith process, we have x3, v1, and v2. Those three vectors are orthogonal to each other, and then we normalize it, and then we can find the organization of the symmetric matrix. Right, so it takes a lot of work. Sometimes we have a space that would have two or more vectors because of multiplicity. In that case, we have to use the Gram-Schmidt process to turn those into orthogonal vectors within that eigenspace. Anything outside of that certainly will orthogonal to the vector in eigenspace. So that should be okay there. But we need to use the Gram-Schmidt process. So yeah, like I said, we will not complete the problem. I just want to show you when we have an eigenspace of more than two vectors and they are not orthogonal to each other, and we have to use the Gram-Schmidt process. Right, spectral theorem. The set of eigenvalues of matrix A is sometimes called the spectrum of A, and the following description of eigenvalues is called the spectral theorem. The theorem is only for symmetric matrices. An n by n symmetric matrix has the following properties. It has n real eigenvalues counting multiplicity. Because like what we have here, for multiplicity we just count like multiplicity of 2, so 1, 2, then 3. Right. The dimension of eigenspace for each lambda equal the multiplicity of lambda as a root of characteristic equation. So in that case, so this one, multiplicity of 2, we do have two vectors. The eigenspaces are mutually orthogonal in the sense that eigenvectors of different space, of different eigenvalues are orthogonal. We talked about this already. X3 on different space than x1 and x2, therefore x3 orthogonal to x1, x3 orthogonal to x2. And of course they can orthogonally, they're organizable, so which what we did. So when we write it down, suppose A equal to A D Q transpose, of course inverse would be transpose, so that's what we have here. So we can decompose like that. Q will be the matrix of orthonormal eigenvectors, so we stack them in column. And now what we do here is we're just going to transpose the row, turn into the column. So that's why I write like that, right? U1 is the first column, turn into the first row. Actually, I just say it. Okay, that makes more sense. Sorry. Right, and then when we multiply together, we have this. So pretty much eigenvalues times eigenvector, the first eigenvector, and then the first eigenvector transpose. And this is called the spectral decomposition of A. And we using the eigenvalues and eigenvectors, and not just any eigenvectors, orthonormal eigenvectors. Right, now we have an example here. Now let's construct the spectral decomposition. So in this case we have, this is lambda 1 and this is lambda 2. Corresponding to lambda 1, of course, is eigenvector u1, corresponding to this is eigenvector u2. So according to this, we can say A is equal to the eigenvalues of lambda 1 and then u1 transpose plus lambda 2 u2 transpose lambda 1 is 8. Right, u1 to square root of 5, 1 divided square root of 5, 1 divided by square root of 5. Then we transpose this, and then lambda 2, the vector -1 divided by square root of 5, 2 divided by square root of 5, and then transpose. Right. 2 times that row times column, so that would be 4 over 5, 2 over 5, 2 over 5, and 1 over 5. One over 5, negative 2 over 5, negative 2 over 5, and 4 over 5. Of course, you see, those are symmetric matrices themselves. Right, combined 8. What do we have? 32 over 5, 16 over 5, 16 over 5, and 8 over 5. Uh, 3 over 5, negative 6 over 5, negative 6 over 5, and 12 over 5. Right. So when we add them, 32 and 3, that 35 divided by 5 is 7. 16 minus 6, 10 divided by 5, 2. That's also 2. And 20 divided by 5, 4. Of course, that is A, right? So show that A can be decomposed into this which is called the spectral decomposition. Right. So as we see in this section, when we have a symmetric matrix, we can decompose that into what we call the orthogonal diagonalization. Even though that seems like a lot of work, but when we find eigenvalues and eigenvectors, normalize the eigenvectors, in that case we can form the orthogonal matrix, which has the very nice properties of the inverse equal to transpose. So we're just going to turn the matrix sideways, we have the inverse. That's a very easy thing to do. And so once again, when we have the symmetric matrix, we can orthogonally diagonalize it. And this is how we do. And the vectors from different space, different eigenspace will be orthogonal to each other. So x3 orthogonal, x2 orthogonal, x2. Those two may or may not orthogonal to each other. In that case, what we do is just simple. Use the Gram-Schmidt process to find two vectors that are orthogonal in this space, and those two vectors and this vector together will form. We can find an orthonormal basis for that, and still will be orthogonal diagonalization. Yeah, I should say two orthogonal vectors in here and another vector in this space. With those three vectors, we can orthogonal diagonalize it. Right, and then of course learn about spectral decomposition. Right, so with that, we finish section 7.1. Thank you for watching, and see you in another video in linear algebra.